let us think about something called factor of safety. And this relates to the fact that the world is full of uncertainty. So you might have a load that you imagine that will be on your structure. You think it'll be so many pounds, but how do we know? The actual load will probably be different. We don't know how much different, but it'll be different. And then there might be some future loads that show up that we don't even know about now. I keep going back to the deck on a house, and what if somebody puts a hot tub on the deck and you didn't design it for a hot tub? That's an unknown load. So for all these reasons, uncertainty and unknowns, designers use an allowable stress that's lower than the actual failure stress, and that gives us a margin of safety. So if the yield stress is where the thing is going to fail, that's the failure stress, that's not the stress you actually design to. You give yourself a margin and you say, I'm going to design to a lower stress just in case. And that ratio between the yield stress and the allowable stress, the stress you're going to allow yourself, that's called the factor of safety. So here's an example. This is the first problem in our quiz. And you know now that the yield stress of mild steel is 36,000 psi. We keep seeing that in tables and in our stress strain diagrams. So yes, we know that mild steel yields at 36,000 psi. But to give ourselves a margin, we only want to allow a stress in our structure of 18,000. Question is, what is the factor of safety? Well, yield stress 36,000 divided by allowable stress 18,000. What's 36 divided by 18? Ha! That's your factor of safety. Here's another one, not quite such an even number. Yield stress of mild steel is still 36,000 psi. That hasn't changed. And let's say the allowable stress in this particular structure is 24,000 psi. What is the factor of safety? No problem. 36,000 divided by 24,000, that's the factor of safety. And you can punch that into your calculator. What often happens, though, is you know the yield stress of your mild steel, and somebody gives you a safety factor. So let's say the safety factor is 2.5 in this particular kind of structure that you're doing. So you need to figure out, okay, how much stress can you allow yourself? Here's our formula. Yield stress over allowable stress is factor of safety. Well, what could you do? You could put that fraction, yield over allowable, into one of these good old triangles. So yield over allowable, we'll put factor of safety into the other corner of the triangle. So now it looks a little bit more manageable. If we're looking for allowable stress, that's the one we would cover up. And look here, we're left with yield over factor of safety. We're left with 36,000 divided by 2.5. That will tell us our allowable stress. I want to point out a number that you will encounter a lot if you're working with steel. In the AISC Manual of Steel Construction, which is all about designing with steel, they give an allowable stress for, especially for columns, but often for beams too. The allowable stress is 60% of the yield stress. Well, what happens if you say 60% or 0.60 times 36,000 psi you get 21,600 psi. So it's very common to see designers use an allowable stress of 21,600 psi for mild steel. And I point that out because if you happen to have the book and you're thumbing through various examples, you'll notice he keeps talking about allowable stress of 21,600, or sometimes he rounds it up to 22,000, which is close. Where did he get that number? He got it from this AISC standard. Some codes, depending on what field you're working in, may specify what the safety factor is supposed to be. We mentioned that AISC says the allowable stress is 60% of yield stress. That works out to, if you invert the fraction, that works out to a safety factor of 1 2/3. In cranes, ASME has standards for cranes, and for running lines, that is the lines that move and they lift loads up and down, the safety factor is 3.5. And for lines that are not moving, that are guy lines, they're just supporting things, the safety factor is 3. Brittle materials, like maybe you have cast iron, brittle materials have a safety factor of 20, but that's based on ultimate strength. Question: if cast iron is brittle, why does it use ultimate strength instead of yield strength when it's thinking about safety factor? Well, you might remember that brittle materials, like here is cast iron, this curvy line in the stress-strain diagram. Brittle materials do not give warning of impending failure. They look fine until all of a sudden they're not fine at all and they break. What makes a material like mild steel be ductile is that it has an elastic range and it gives warning. Things are starting to stretch. It gives warning before it yields, but cast iron doesn't. It just the yield range is so small you don't notice it. Well, anyway, let's go on to the next quiz question. So here we are. This is a really wonderful drawing. Here's a weight, a load hanging from a cable. That's what that's supposed to be. So the cable is 20 feet long. It has an area of 2 square inches, and this cable weighs 5 pounds per foot. That's a heavy cable. Question: what is the stress due to the cable's own weight? Okay, what is its weight? Well, let's see. It's 20 feet long. It weighs 5 pounds per foot, so that cable must weigh 100 pounds. Okay, now we can move along. What are we given? We now are given the force, the weight, because we have 20 times 5 is 100 pounds. Okay, the weight of that cable is 100 pounds. What else do we know? We were told that the area is 2 square inches. And what are we trying to find? The stress. Oh, look. Our familiar stress equation. Stress equals force over area. Stress is pounds per square inch. So there's our equation. 100 divided by 2, that will give us our stress. Yay! Let's go on to the next question. This steel cable has an ultimate stress of 60,000 psi, but you want a safety factor of 3 because it's got a weight hanging from it. So figure out what is the allowable stress. Alrighty. Well, what are you given? You are given that the ultimate stress, the stress where this thing just breaks, the ultimate stress is 60,000 psi. And you're given that it has a factor of safety of 3. And you are trying to find out the allowable stress. Okay, so what equation will you use? Let's go back to our triangle where we know that factor of safety is the whatever stress you're working with, the ultimate stress in this case. In a previous problem, we put yield stress up here. In this problem, we're putting ultimate stress here. Anywho, factor of safety is ultimate stress over allowable stress. Okay, and we're looking for allowable stress, so we'll cover up the one we don't know. And that leaves us with ultimate stress divided by factor of safety. That will give us the allowable stress. So you can plug 60,000 psi divided by 3 into your equation, and you'll find out your allowable stress, which should be 20,000 psi. All right, and the area we already know is 2 square inches. Question is, how much total weight can this cable support? And let's say this is a crane out on a job site, and you want to know, okay, you got the weight of the cable and you got the weight of whatever it is you're lifting. What is the total weight that this thing can support? If you're only allowing yourself 20,000 psi, what are we given? We know the area is 2 square inches. We know the allowable stress, which we just figured out, is 20,000 psi. So we're looking for the weight, which is P. Stress is force over area. Okay, and we're looking for force, so we'll cover up that one. And we're left with stress times area. There we go. Force is stress times area. Yay. Now let's go on to this last question. It's this same crane here where we have the cable, and we figured out earlier that the cable weighs 100 pounds. And in the question we just did, hopefully you figured out that this thing can support a total weight of 40,000 pounds. But that's the cable and this load that's hanging from the cable. Let's find out what is the load that this thing can support. And the load is this beautiful trapezoid looking shape. It's the thing that's hanging from the cable. Okay, so what? We're trying to find out the maximum load that we can hang from that cable out in our crane. And we are given the total weight, well given, we figured it out in the previous problem. The total weight, 40,000 pounds. And we figured out that the cable weight is 100 pounds. So how are we going to figure out how much weight we can hang from that cable? Well, we've got the total weight, let's say maximum load, this load hanging from the cable, is the total 40,000 pounds minus the cable, 100 pounds. That'll give us how much can we put on this load right here. Yay!